Okay, so so the last thing that we missed in the previous section was we were talking about functions, and in some sense these are the simplest functions, sequences. Okay, so a sequence is you have the numbers, you have the natural numbers, 1, 2, 3, 4, 5, 6, blah, blah, blah. And then to each natural number, you associate you associate a new value, right? A of 1, A of 2, A of 3, A of 4, blah, blah. And this map A is a sequence. Maybe I should call it F. But usually with sequences, you don't use F. You use A's and B's and C's. Okay. So a sequence, for us, a sequence is a map, a function, a function A, going from the natural numbers into the reals. Okay. It takes some number to something called A of n. And usually, just to put a remark here, usually one writes A sub n rather than A of n when you're dealing with sequences. You say instead of calling this A of 1, you call it A sub 1. A sub 1, A sub 2, A sub 3, A sub 4, blah, blah, blah. Okay, so for example, right, if I could have, say, A sub n, let A sub n be 2n. Okay, for all n, for all n, 1, 2, 3, etc. Okay, and what would that be? Well, A sub 1 would be 2, A sub 2 would be 4, A sub 3 would be 6, etc., etc. And you see that this would be the sequence of even numbers. Right. So, right, the picture is like this, right? You've got 1, 2, 3, 4, 5, etc., etc. And then A maps those guys onto 2, 4, 6, 8, 10, blah, blah, blah. Right? That's the picture, the mapping. Right? And what this mapping shows you, yes?
What does the word say next to arcane?
Remark, usually. So what this shows you is something, I don't know if it's interesting or not, but it shows you that there's many, this is one way of thinking that there are as many even numbers as there are natural numbers. Okay. There's many even numbers as there are natural numbers. Right? You can find, there's a way of associating to each natural number, one and only one even number. Right? So there's the same size infinity, right? Of course, there's infinitely many of these guys, and there's infinitely many of those guys. But what this shows you is that infinity is the same infinity. Okay. Let me give another example. You could have A sub n defined like this: n plus 1 over 2 if n is odd, and negative m over 2 if n is even. Okay. Take a minute and tell me what this sequence looks like. So n again is in 1, 2, 3. case. So what do you get, Isaac?
A sub 1 is 1, A sub 2 is -1, A sub 3 is 2, A sub 4 is -4. My bad, it's -2.
-2, yeah. And so on and so forth. Right? You're going to get 1, -1. So your sequence looks like 1. If we start at 0, A0 is going to be 0. So 0, 1, -1, 2, -2, 3, -3, etc. is the sequence that this thing outputs. Nora?
So you combine the two sequences and write them together, rather than writing them separately?
This is just one sequence. This is just one sequence, right? Here it is. What's the first element? 0. What's the 0th element? 0. What's the first one? The second one is -1. The third one is 2. The fourth one is -2, etc., etc. It's just one sequence. Yeah. Okay. And what you see with this is that the number of integers is the same as the number of natural numbers, right? Even though you might think there are more integers than natural numbers, well, there's a way of making a one-to-one correspondence between them, right? And so this infinity is the same as that infinity. Okay. We're not going to do it, but it's actually possible to make a sequence that gets you all of the rational numbers. All of the rational numbers. So you might think the rational numbers, maybe you think that's sort of a bigger infinity than the natural numbers. But in fact, it's the same infinity. Okay. The question is, what do you think about R? Do you think we can get a sequence that will cover all the real numbers? The answer is no, it's impossible. It's impossible. This is actually a different kind of infinity, right? This is actually a bigger infinity than that infinity. Okay, and maybe we'll talk about that at some point, but it's not at all relevant to the course. Okay. Yeah. So just for your amusement, you're not here to be bored. Okay. Okay. Yeah. So actually, there are different kinds of infinities. Some are bigger than others. Okay. Okay. So there's not much to say about sequences. There is this thing called a recursively defined sequence. Recursively defined sequence. And it's the way you create this sort of thing is you define the first couple elements of it, and then you define the later elements in terms of the previous elements. Okay, so first set the values for the first couple of elements, and then the later guys will depend on the previous guys. So the most famous example is the Fibonacci sequence, right? Fibonacci sequence, right? And what you do, the way you define it is you say, well, let the first element be 1, so let a sub 1 be 1, let a sub 2 be 1, and then for n bigger than or equal to 3, let a sub n be defined as the sum of the two preceding guys. Okay. Please.
So for those, do you have to do all the ones before that in order to get the next number? Like if you were just given 7, you can't just do that. You have to do.
That's right, because it's recursively defined, right? So A7, you'd be like, what's A7? Well, I know A7 is A6 plus A5, right?
But you have to.
But I don't know what A6 is. Well, A6 is A5 plus A4, A5 is A4 plus A3. And you have to go all the way back down to the A1 and A2 to get this. Yeah. So that's the trouble. So, right, and so if you're building it, you build it from the bottom up, right? You say, well, what's A3? A3, well, the index is bigger than or equal to 3, so I know that A3 is going to be the sum of its two predecessors, right? And so it's 1 plus 1, it's 2, right? What's A4? A4, well, again, the index is greater than or equal to 3, so I know that it's the sum of its two predecessors. Now I know what A3 is, right? A3 is 2, A2 is 1, right? And so I get 3, right? And in this way, you bootstrap your way up to whatever number you want. Okay, right? So A5 is going to be the sum of its two predecessors, right? A6 is going to be the sum of its two predecessors, and so on and so forth. Okay, but you can't just jump to somewhere and say, tell me what the 1000th Fibonacci number is. Okay. Although there are ways of making guesses. There are ways of making guesses. At least you can estimate the size and stuff. Those of you who like this sort of thing, Fibonacci numbers are supposed to, show up in vegetation, like pineapples and stuff. Supposedly, you can find the Fibonacci numbers on pineapples, and they use them in the stock market. I think that's nonsense. But yeah. But anyway. Okay, so that's that. Okay, so. I guess I shouldn't say it's nonsense. I haven't looked at it. But my gut reaction is it's nonsense. Okay, so section 1.5, polynomials, geometric functions, and combinations of functions. Combinations of functions. Okay. Yes.
For a recursively defined sequence, is it enough to write some examples like A3, A4, A5, A6, or do you have to write out a rule of AN equals?
Well, I mean, to specify the whole sequence, you would have to give a rule, right? You'd have to give this rule where you define everybody. So if somebody says define the sequence, right? Well, you need to be able to specify every number in the sequence, right? So the way we did it for the Fibonacci guys is we said we told you what A1 and A2 were, and then for A3 and above, we defined them in terms of the previous two guys, right? So you do need to give a rule, and you need to give the initial elements, because if you change those initial elements, well, you've changed your whole sequence. Right? Like if we had started off with, say, A1 is 2, and A2 is 7, say, right? Well, then A3 would be 9, A4 would be 16, A5 would be 25, right? A6 would be 41, etc., etc. Okay. So. I'm sure you all know what polynomials are, but we're just going to define them again. So any function of the form, any function p, say, of the form px equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a1x plus a naught, where these ai guys are real numbers and an is non-zero, is called, and n is a natural number, is called a polynomial of degree n. Right? And you know, right, the ai are called the coefficients, the a sub I are called the coefficients. So anybody who looks like this is called a polynomial, right? You know it. Like, you know, if I said x squared plus x plus 2, that's certainly a polynomial because it falls into this form, right? N would be 2, my a2, right? Here would be n is 2, my a2 is 1, a1 is 1, and a0 is 2. Right? The coefficients are 2, 1, are 1, 1, and 2. Right? The degree is 2. Is that clear? That this actually is a polynomial? Maybe it's not. I think when I first saw this, I was confused. You know, why is this a polynomial? But I hope it's pretty clear. Anything that looks like this is a polynomial. Any polynomial is going to look like this. Right? This is the general form of a polynomial. Everybody looks like this. All polynomials look like this. Isaac?
So polynomials they can't have a negative or a subtraction in them?
That's right. You don't have it. Oh, wait.
Like, I mean, it can't be x squared minus
No, that's
x.
fine. That's fine because the coefficients just need to be real numbers. So if I have negative, then my a1 coefficient is -1. Okay, it's plus -1. Okay, yeah. But you can't have what I thought you were saying was that you can't have negative guys in the powers. So no polynomial has like you don't have x to the -1 plus 2 as that's not a polynomial. Okay. Yes, Nico.
So is the a to the n minus 1, is the n minus 1 just identifying like what term that is, or are you like specifying what?
Yeah. This is just an index. Like here's the 0th coefficient, the 1st, 2nd, 3rd, blah blah blah. The n minus 1th, the nth. Right. This is an n. If this is a degree n. If this is a degree 2 polynomial, it's going to have a 0 coefficient, a 1 coefficient, and a 2 coefficient. Okay. If it's an nth degree polynomial, it's going to have 0, 1, blah blah blah, up to a sub n. Okay. Now some of these might be 0, right? Right. If for example I had something like this, then my constant coefficient is 0. Okay. But it's there. It's just 0. Okay. Okay. Number 2, if p of x naught is 0, we say x naught is a root of p, a root or 0 of p. The roots of polynomials, where the polynomial becomes 0. Right? For example, if my p is x cubed plus 3x squared plus 7x plus 10, p of -2 is actually 0. So -2 is a root. -2 is a root. It's not going to work.
What does this say when it's very, very long?
Sorry. Yeah. If p of x naught is 0, we say x naught is a root of p. X naught is a 0 of p.
Okay, and then under that?
A 0. A root of p or 0. A root or 0 of p. Okay. Okay. Everyone all right? Any other questions? Okay, so now I'm going to give you just a fact. This is called the Fundamental Theorem of Algebra. Fundamental Theorem of Algebra. Every polynomial with real coefficients can be factored into a product of irreducible polynomials of degree less than or equal to 2. Okay, and I'll explain what irreducible means in a second. Okay, here is the, to sort of illustrate what this means, let's go back to this guy here. Okay. Here's a polynomial, x cubed plus 3x squared plus 7x plus 10. Actually can be factored into a product of polynomials of degree less than or equal to 2. It turns out to be equal to this product. This polynomial can be factored into a product of factors where all the guys are of degree less than or equal to 2. Okay. And further, no one can be factored any farther. This cannot be further factored in R. So I'm going to rewrite this to the people in the back. Further, so this cannot be further factored in R. This guy here. Okay. So given any polynomial, you can actually break it down into pieces, all of which are degree less than or equal to 2, and the pieces that, the ones that are degree 2 can't be broken down into smaller pieces over R. Although if you went to the complex numbers, you could. If you're in the complex world, everything breaks down into products of degree 1, products of factors of degree 1. But in the reals, you can't do it. If you try to do this using the quadratic formula, you'll see that your roots are imaginary or complex. Okay, so this is just a fact that will be useful to us at certain points. So you've probably seen this thing before. You have a polynomial, and you can break it down into factors. But to prove this, actually, is not so easy. Like if you take more math, you'd have to take, if you took 4 more classes, wait, let me think. 1, 2, 3, 4th. Yeah, at the 4th class, then we can explain to you how this works. Okay, but not before that. No. Maybe 3. If you took a shortcut, you could sort of. If you took Calc 1, Calc 2, and then you skipped Calc 3 and instead went to linear algebra, and then from linear algebra you went to this course 135, complex analysis. You went to complex analysis. Complex analysis, really cool course. It's sort of like doing calculus with complex numbers, and you're trying to understand everything that happens. It turns out that sort of incredible things happen. Okay. Anyway, in that course, there's a simple way of understanding why this happens. Yeah. So you're not far off. Okay. So let's go on. So polynomials, basic fact about polynomials, and then just a sort of side comment about odd and even. So odd and even. You've probably seen this before, right? If f of negative x is the same thing as f of x, we call f an even function. if f of negative x equals negative f of x, we call f an odd function. Even functions, odd functions. Can somebody give me an example of an even function? Go ahead. X squared, right? So for example, x squared, right? If I plug in -3, I get the same thing as f of 3, right? -3 quantity squared, the same thing as 3 squared. Right? Somebody give me an example of an odd function. Okay.
X cubed.
X cubed, right? X cubed will do. Right? Certainly, if I take negative x and I cube it, I get negative x cubed. Right? No matter what number you put in, negative that number cubed is going to be negative the cube of that number. Right? -2 cubed is negative 8. Negative 2 cubed. Can anyone give me, so you notice something, why do we call these things even and odd? Because if you look at the degrees, right, if you have a polynomial that has only even degrees in it, it's an even function. Right? If you have a polynomial that has only odd degrees in it, well, it'll be an odd function. Right? If I have this, right, something like that, that's going to be even. Right? If I throw on more odd guys, right, that's going to be odd also. Right? Can anyone give me an even function or an odd function? An even function, say that it's not a polynomial. Absolute value, great. Kayla?
Sine.
Sine? Let's see, so the sign is what? Even or odd? It's even, yeah. Oh no, it's odd actually. Sine is odd. Sine is odd. Cosine is even. Yeah. Yeah. Now later on, not too far away, in fact, in the next course, what you'll see is that the sine actually can be expressed as an infinite polynomial. So on and so forth. The sine actually has an expression as an infinite polynomial, all of which, where all of its components are odd. Okay. So it's actually the sine, although it's not a polynomial, it's actually this sort of infinite polynomial where everybody's odd. And the cosine similarly will become composed of all even parts. Okay, but again, we're not going to explain that. You'll see it in the next class. Where you talk about what it means to add an infinite number of numbers. Right? Because what does it mean to add? Right? If I've got this infinite polynomial, how do I add them? How do I add it? Right? Or how do I multiply it? Okay. Okay. Generating new functions from old functions. Okay, so there's a simple way. Functions and algebraic operations. Functions and algebraic operations. So this is just really a notation, right? I'll explain by example. If f of x is x squared minus 2 and g of x is x plus 3, then if I write f plus g of x, what's meant by that is f of x plus g of x. Right? So that would be x squared minus 2 plus x plus 3. Okay, so the sum, this you can create the sum function. You create a new function. It's just you add the outputs of the original guys. If I write 5fx, if I write 5fx, what I mean by that is 5 times f of x, right? So that's going to be 5 times the quantity x squared minus 2. So you can, what does it mean? You create this new function called 5f. That guy is the one who just gives you 5 times what f would have given you. So nothing fancy. If I say f over g x, that's another function. What's it going to give you? It'll give you f of x. What f of x? It'll give you the quotient of f of x over g of x, right? So it'll give you x squared minus 2 over x plus 3. So this is basically just notation, just notation. Okay. Any questions? Any questions? It's pretty straightforward. More sophisticated. So-called composition. So, right, just slightly more sophisticated. You have one function, and then you have another function following it. Okay. So, so for example, so let's say that f of x is x squared plus 1, g of x is the square root of x. Okay. If I write something like g composed with f of x, what I mean by that is that you take the output of f and you feed that into g. Right? So here, in this example, it's going to be the square root of x squared plus 1. Right? Because you take the output of f and you feed that into g. Right? So you take the output of f, you get x squared plus 1, you feed that into g, and you get the square root of x squared plus 1. Okay. And so those two guys together are called the composition map. Okay. It's written G composed, this is read G composed F, G composed with F. Take 1 minute and tell me what F composed with G would be. Okay, turn to somebody nearby and say, it's this.
It was never squared. I don't know. Yeah, well, because like you said, how you already came about.
Okay, what is it? What is it? Isha? X plus 1? Everyone got that? X plus 1, right? Because f of, g is the square root of x, right? So you get f of the square root of x, right? So, and f says, I'm going to square whatever you give me and then add 1 to it, right? So I'm going to square whatever you give me, and then I'm going to add 1 to it, right? So it'll be x plus 1. One note of caution, what's the domain of f composed with g? All non-negative numbers, right? Because g is the square root function. It can't take negative numbers. Even though the composition looks like it could take any sort of number, right? But actually g doesn't take negative numbers. Okay, so you have to be a little bit careful about when you're looking at the domain. Okay, so be careful, remark, be careful with the domain. Right, the domain of f composed with g is all points in the domain of g whose images lie in the domain of f. Right. You have to see, they have to be points that make sense for g and whose images make sense for f. Whose images make sense for f. Okay. So let me just say one small thing, which is something I'm pretty sure you've seen before. You have these things called translations. Right. So given a function f, one can define a translation of f, where you take g of x to be f of x plus some number. Okay, f of x plus some number, or for example, you could have g of x being f of x plus some number, or this sort of thing. And this amounts to like sliding the graph either horizontally or vertically. Okay. I don't want to talk too much about it. It's not that important here. So, but I just want to mention. Okay, so that's it for today. We didn't get to the very last thing, which is parametric curves. Okay, so I'll send out an adjustment later, but don't do anything in the assignment that involves parametric curves. That we'll save for the next class.